Okay, so as I said in the previous video, we're going to learn how to find the surface area of revolution. So right here, I'm telling you that when you revolve a curve about an axis in space, you actually create a surface of revolution. And the area of the surface depends on the length of the curve and the distance each of its segments are from the axis of revolution. So you can actually research, a kind of a long drawn out explanation of where this formula comes from, but basically it comes from adding a lot of the areas together, and therefore you get the integrals that we're going to talk about here. So let me just give you the formula. I'm going to give you two formulas. The first one is the formula for the surface area for revolution if you revolve something about the x-axis. So first of all, if the function is greater than or equal to 0 and is continuously differentiable, in other words, you can differentiate it on the closed interval from a to b, then the area of the surface generated by revolving the curve around the x-axis is actually equal to, so S is for the area, the surface area, is actually equal to the integral from a to b. It's actually the integral from a to b, and that's on the x-axis, x equal a to x equal b, 2 pi times y times the integral 1 plus the derivative of y with respect to x quantity squared dx. Now, we generally don't want y in a integral for delta x, for dx. So actually, we're going to think of y as its function value in terms of x. So basically, y is the same as f of x, as you know. And also, dy over dx is actually the same as f prime of x. So this is just another way to write the formula. Okay, so let's go to our first example. So I want to find the surface area generated by revolving the line y equal x from 0 to 2 about the x-axis. Okay, so let's take a look at my picture. Okay, so here's my y equal x line, and it stops here where x equal 2. So here x is 0, here x is 2. Now if I revolve this around the x-axis here, then let's just look at a cross-sectional view, like if we sliced it in half. And this doesn't line up perfectly, but hopefully you can see the cross-sectional view would look like a triangle. Well, if you think about it, basically when we revolve it around the x-axis, we're going to get basically a circle here. And so what you've got here really is a cone. So you've got a cone that has a surface area here that's generated. Now the base of the cone doesn't have a surface area on the base. I'll address that in a minute. But what you're going to do is, I'm just trying to give you a picture of what you're going to have if you take this line and revolve it around the x-axis and show you what you've generated. Now, so to use the formula, okay, so we know f of x is x, and therefore we know f prime of x is 1. And also we know a is 0 and b is 2 because we're integrating from x equals 0 to 2. Okay, so putting it in this formula up here, we would have the integral of 2 pi, right? So I went ahead and factored the 2 pi out of the way to get out of my way. And then we have f of x, which is x, so we have x. And then we have the square root of 1 plus the derivative of f of x, which is 1 squared. So that's just going to give me the square root of 1 plus 1, which is just the square root of 2. So I'm just going to have x times the square root of 2, and I'm going to integrate that. And so that would give me x squared over 2 times the square root of 2, and then also times the 2 pi that I have out here. And I went ahead and simplified this, canceled the 2's, so I actually get pi times the square root of 2 times x squared from 0 to 2. Well, if you evaluate this from 0 to 2, if you evaluate at 0, you just get 0. But if you evaluate at 2, you're going to get 4 pi times square root of 2. And so that's it, 4 pi times square root of 2. Now, there's a formula for the volume of a cone, and I'm sorry, did I say volume? Area, the surface area of a cone. So you can actually find the surface area of a cone from this formula, where r is the radius of the cone and h is the height of the cone. Okay, so you can freeze the video if you want to and then just check my calculations, but I just want to point out that when I plugged a height of 2, which is the height of our cone, and a radius of 2, I actually got 4 pi plus 4 pi times the square root of 2. So your first question may be, well, wait a minute, that's not the area you got up here. Well, actually, the area up here does not include the area of the base. Remember, I told you we wouldn't be getting the area of the base. We would just be getting the area of the surface that's generated by revolving this around the x-axis. So this formula actually does include the base. So if you take off the area of the base here, which would actually be the 4 pi, then you actually do get the same answer that I got up here for the surface area. Okay, so we're going to go ahead and do another one about the x-axis. Okay, so it says find the area of the surface area when you take the curve y equal 2 square root of x from 1 to 4 and revolve it around the x-axis. Okay, so right here is the curve y equals square root of x. So that, y equals whatever it was, 2 square root of x. So that's that curve, and we're actually just doing it from 1 to 4. So we're only doing a partial piece of that. And then we're going to revolve that around the x-axis, and we'll get a solid. And so we want to get the surface area. So going back to the formula, I know that the distance that this function is from the x-axis is just f of x, which is 2 times the square root of x. And I'll let you differentiate this, but I went ahead and differentiated. I got 1 over square root of x. And then we're integrating from 1 to 4. So now I'm going to have, again, I'm going to pull my 2 pi outside. I like to keep it outside the integral. And then I'm going to integrate from 1 to 4. I'm not sure why I have 0 to 2 there. Probably just copied from down, but all of these should say 1 to 4. So let me just break away from this and fix that. Of course, it won't seem like I left very long to you, but let me fix it. Okay, so I'm back. All right, so I have 2 pi, and so what I'm going to do here is I'm going to integrate, as I said, from 1 to 4. And so the function, I have the function 2 times square root of x, and then the square root of 1 plus 1 over square root of x quantity squared. Okay, so now let's do some simplification here. If I square 1 over square root of x, I just get 1 over x in the radical. So now what I'm going to do is I'm going to write this, get a common denominator, and I can write this as x plus 1 over x. So I'm going to do that there. Okay, and then if I take just this portion out, well, I'm not really taking it out, but if I rewrite this as square root of x plus 1 over square root of x, then I can put the square root of x here under this square root of x, and that allows me to cancel those. And then the next step, I'm going to factor the 2 out here with the 2 pi, and that'll give me 4 pi. And so now all I have to do is integrate x plus 1 to the 1/2 power. And when you integrate that, you get x to the 3/2 times 2/3. And so, and then you have that multiplied by 4 pi. And so when you multiply 4 pi times 2/3, you get 8/3 pi. And then I have the x plus 1 to the 3/2. So now I'm just going to evaluate this from 1 to 4. And I'll let you do that on scratch paper if you want to. So, plug 4 in here and see what you get. Then plug 1 in here and see what you get. And then take the difference of the 2. And I went ahead and just gave you the exact answer, because many times the instructor will want you to give the exact answer. And the reason they generally do that is to make sure that you didn't use some sort of a technology. to get the answer, because usually if you give the exact answer, then you know, you must have solved this using calculus and not technology. Okay, on the next examples, I'm just going to show you how to set these up. And so, but first of all, what if you're revolving around a curve around the y-axis and you want the surface area? Okay, well, you just sort of interchange here in the formula. You're going to integrate from y equals a to y equals b 2 pi x, which is the same as 2 pi times your function of y, so you have to have a function of y, and then the square root of 1 plus the derivative of x with respect to y quantity squared, as opposed to, you know, dy over dx, it's dx over dy. Or in this formula, it would be the square root of 1 plus g prime of y quantity squared dy. So let's go ahead and look at a formula. So look at an example. It says find the area of the surface generated by revolving the curve y equal to square root of x. So that's the same curve from x equal 1 to x equal 4. Now, I said x equal 1 to x equal 4 here, but let me explain that, because we can get the y values from that. All right, so look, here's the curve right here, and I'm going to revolve that curve around the y-axis, and basically it's going to give me something probably shaped like this. All right, and it's going to, you know, be a circular. So it's kind of like a cone. It's kind of a cone shaped, maybe an upside down bell or something like that. Okay, now I gave you a hint here. See, if x is 1, you can plug the 1 in here and get y equal 2, and if x is 4, you can plug 4 in here and get y equal 4. So remember, I told you you needed y values, so that would, going from x equal 1 to 4 would be equivalent to going from y equal 2 to 4. Okay, so now what I have to do is I have to solve this for x. So if you square both sides and then divide by 2, you'll get y squared equals 4x, and then divide by 4, not 2, but 4, divide by 4, and you'll get that g of y is y squared over 4. Okay, and then the derivative of that would just be y over 2. So I used c and d here, even though the formula says a to b, but it's the same thing. So I'm going to integrate from 2 to 4. So we're going to integrate from 2 to 4, 2 pi times the function of y, which was y squared over 4, times the square root of 1 plus y over 2 quantity squared. And then the rest of this is just simplifying. So I just did some algebra here to simplify this, and I finally got it into this form. So this is the most I could simplify it. And then if you integrate this function from 2 to 4, then that will give you the actual surface area that we're looking for. Now, some texts will actually call this C and this D to avoid confusion. So, but I left it as A equal A and B. You just have to know that these are y values. Y equals A to y equals B. So therefore, but down here I called them C and D kind of out of habit. Okay, so the next one, we're taking this x equal 2 minus y, and we're going to revolve it around the y-axis. So it looks like we're getting a cone again. And we're going to go from y equals 0, which would be here, up here to y equal 2. So we go there, and then let's see. We know that g of y, I have to do this quick. G of y is 2 minus y. The derivative of that's minus 1. And we know we're integrating from y equals 0 to y equal 2. So put that in your formula, and so you get the integral from 0 to 2 pi. G of y is 2 minus y, and since g prime of y is negative 1, you put the negative 1 squared in there. And then the rest of it is just simplifying the radical. And when I simplified that radical and then integrated here, I got this function. And then I finally got an answer of 4 pi square root of 2. So go ahead and work through that integration to get the same answer I got. On the next video, I'm going to talk about parametrized curves.